We want to do another example problem of general surface integration where we're going to look at the consequence of projecting onto one axis versus another. So it's a relatively simple problem in one case, but I want to show you how sometimes one of the two options, even though they both have to work, one can lead to a much more difficult integral or messier integral than the other. And we'll just see that. So this is actually example 3. It's actually an example in the textbook. They don't do it both ways in the textbook, but that's where it is in section 913. So this is kind of, again, before we get to flux integration. So the problem would simply stay, or the way the problem would be formed is this: evaluate this integral. So double integral s xz squared ds. The s's indicate this is a surface integral, otherwise you'd be told that in the problem, but you have to have some context. This is a surface integral. For s being the surface, which also indicates surface integration. So s is the portion of y equals 2x squared plus 1 within the first octant and bounded by x equals 2, z equals 4, and z equals 8. So that would be what the problem would say. Just that part. Okay? That's the problem statement. And so you have to make sense of that, and like always, we have to plot this. One thing we'll say, just to be clear too, so the thing that we're integrating over the surface is the xz squared function. It's defined in all space. We're only going to care about it as it varies over the surface. And then what is the surface? That's the second functional definition. It's as usual, defined by a series of limits. Okay, so we have x between 0 and 2. We know x is 0 because in the first octant. So we know x, y, z are all positive. I know x has an upper limit of 2. Z goes from 4 to 8. Y is defined as 2x squared plus 1. So that surface doesn't depend on z. So we know we have sort of, it's like a curtain hanging vertically with no z dependence at all, which we'll draw. Okay. This is, I do this ahead of time because it's a little bit trickier to draw, so it takes a bit of effort. This is the surface. It's like a sheet hanging, okay, just hanging in space. No variation in the z direction, so it's hanging in the vertical z direction. It bends out. This functional form here is y equals 2x squared plus 1. Okay, and then it comes out to a maximum of x equals 2. That's where this plane cuts it off. And then z, it's only z4 to 8, so it doesn't go all the way down to the xy axis. It's true that when you think, if x is 2, the maximum value in y is 2x squared 8, so it's 9. So this upper limit here, which is defined by this x equals 2 plane, also defines the y equals 9 plane as an equivalent statement on the upper end, which we'll use later when we do this the second way, or just set it up the second way. Okay, so surface. Nowhere in here is included the definition of capital G, because it doesn't matter. This is just the surface. This is we're integrating over the surface. Okay. Now, so we'll start this up. We're going to decide to integrate this. So the first thing is, you can't do this one as an integral over the xy plane because there's no, it projects down just as a line, so you lose the surface information. So the only thing we can do is project onto the xz plane or the yz plane. We're going to project onto xz. So this is the region that's going to sit over top of. So we have y as a height function over this region, which is rectangular. Right? It goes from 4 to 8 in z and from 0 to 2. The diagram's not really to scale, especially in the vertical direction. Okay, so that's what we're dealing with. So let's go ahead and start to build the integral. Okay, I'll leave the diagram up as we go. So we're going to eliminate y. That's one way to say it, or think of the y as the height function over the xz plane. Okay, so this integral then turn into, okay, so we're going to have we are going to integrate over r, yeah. Then we have g, erase this, g was, what was it, x z squared. Okay, so we don't have any y in g. G was independent of y, so that makes this, okay, so this is just xz squared. If there was any y in there, we would replace it with 2x squared plus 1. We would eliminate y's in favor of x's and z's based on the surface. Okay? But in this case, capital G doesn't depend on y. It depends on the surface because it depends on x and z, but it doesn't depend on y. Okay? So then you would have the square root of 1 plus, then we'd have the partial of y with respect to x squared plus partial of y with respect to z squared. Okay, and then we'd have some dx and dz, because that's what we're going to integrate over. So again, this is pretty simple. I'm getting a little bit quicker here than we did in the previous example because we've seen this a bit. So y equals 2x squared plus 1. So the partial of y with respect to z is 0. Okay. The partial of y with respect to x is just 4x. So this becomes x z squared 1 plus, so the derivative here would be 4x, so that's 4x squared, so 16x squared, right? So 16x squared. Okay, and then we have, doesn't matter which way we write this. I'm actually going to do the z integral first. I'll switch order, but that's not critical. Now, right now, we can put the limits now. So let's say the limit on z, well, it's 4 to 8, because that's z, and x is 0 to 2. Now, right away, we see that we can do something that we have an eye for. I can separate this z, because the limits of integration are constants and don't depend on the functions, or on the variables, so then z squared can be brought out. So this can be brought into an integral of z squared dz times an x integral Okay. So that's cool. Here, I'll just do this one more at the very bottom here. So this will become okay, and then we have this same thing here of dx. Okay, and I'll just continue right here. Okay, so that becomes, so this thing becomes 8 cubed over 3 minus 4 cubed over 3 times x equals 0 to 2, and we're going to let u equal 1 plus 16x squared, so du equals 32x dx, so x dx is du over 32, so this becomes 1 over 32 u to the 1/2 du. Okay, so this thing would be, and this guy's what, that 512, that's 256, so, oh sorry, no, that's 64. So we would have 512, okay, sure. 3, not important. Okay, we're going to do the integral now here. So we got 1 over 32, and then I've got u to the two. Okay, so that is what we got here. So my note here, 448. Obviously, this noodling around with these numbers in front is not the most important thing in the world. As part of this particular problem, so we're going to have 2 over 396. So this is 2 over 96. Not important. Now we'll put back the u, so we got 1 plus 16x squared to the 3 over 2 from 2 to 0. Okay. So this thing becomes, I got this. This would be, you could just leave these sort of things, but I've got this as, okay, sure, 896 divided by 288, kind of a bonkers number. Okay, so then let's be careful here. So let's do this. We got the first term, 1 plus, just do this a little carefully, 16 times 4, so 64 to the 3 over 2 minus 1. Yeah? Okay. You could probably almost leave it like that. Okay, actually we're basically done here. I've got a note here that says, actually I'll just finish it up right here. I've got a note here. You don't have to, you could, on an exam, you could leave it like this. It's fine. This happens to be 28 by 9, and then 65 to the 3 over 2 minus 1. Okay, whatever, I guess. So that's fine. It's a weird number, but again, positive. Does it make sense as positive? Yeah, it makes sense as positive because the g function is x and z squared, and we're in the first octant, so g is positive. So I know I should get a positive number. That's good. Beyond that, does it make sense? Hard to say. It should be a pretty big number because I'm integrating numbers where x's and z's are not quite 10, but they're all larger than 1 most of the time, and I've got z squared, so this is probably on the order of tens and tens. So the fact that this is on order of maybe 1,000, it's maybe about right. So fine. So okay, that's another example of a surface integration. What I want to show you now, just in setup, because it'll get bad quick enough, is we decided to project this onto the XZ plane. What if we didn't? What if we projected onto this plane over here? Okay, projected down and thought of X as a height over the YZ plane. Seems perfectly fine. It's still a rectangular region. You'd have this sort of region here. Here would be there. Okay. Let's just see what this looks like. And I can see the point being like how it can kind of get messy pretty easily. Okay. So if we instead eliminated X, so project onto YZ plane. Okay, so the first thing you have to do is the surface is defined with these limits, but y equals 2x squared plus 1. So you have to get that as x as a function of y, because now we want this to be a height x above y. Okay? Above y and z, but it doesn't depend on z. So y equals 2x, this means that we had 2x squared equals y minus 1. So x squared equals 1/2 minus 1. So x equals square root, square root 1 over 2 y minus 1. I gotta tell you, right off the bat, that should make you go, I don't like that, right? Because as soon as we got this, and x is a square root function, it often gets gross. But let's just continue. Okay. So what we would do, right, is we'd have to say, okay, so our limits are going to be z from 4 to 8, and y from when x goes to 0, so it looks like 1 to 9. So we've got 1, y, 9, and then the same thing as we had before for z. Okay. So our integral would become this, and now we have to limit x inside here. So we have g, well I'll just write this for a second, g ds. Okay, so this thing would look like, let's just say this is going to be r, and it's going to be our yz version. Okay, so I've got xz squared. So now I've got this guy, so I've got to say, first of all, it's 1 over 2 y minus 1 to the 1/2 z squared. And then I'm just going to leave it. I'm going to write ds for a second. I'll just expand this for a second. So ds would be, right, 1 plus the partial of our h function, which is x as a function, so x as a function of y squared, plus the partial of x as a function of z squared, right? So that's what we're going to have ds. Now, again, this one's 0. That's good. But dx is a function of y. So dx dy, so d by dy of 1/2 y minus 1/2, right, becomes 1/2 y minus 1 to the minus 1/2 times y, so 1/2. So this becomes 1/4, 1/2, y minus 1. Just be careful here. Right? So that's going on there. Okay, right? Just double checking here. Minus 1/2. Yep. So then this integral here, maybe I'll just write it over here. Okay, so this guy here, right, would become equal to, so I've got dy dz. I've got this initial thing, 1/2 y minus 1, 1/2 z squared times 1 plus that guy squared minus 1 all to the 1/2 dy dz. Okay, and if I'm doing y first, I've got y from 1 to 9 and z from 4 to 8. Okay, I don't think I even need to go for, this is much more difficult, especially the y. The z integral is the same. Oops. the z integral is going to give us the same answer. I can pull the z's out, right? And I would have this as 4, 8 z squared dz. But then I have this horrible thing. All the y stuff. Right? So, not that you can't do it. I haven't tried. Actually, didn't really try very hard to continue on with this. But it's a messy, messy thing when we try to integrate this y. And what would happen is, so when you're doing the problem, you don't always know. Now, when we very, very first started it, as soon as we got here, that's kind of the first hint, like that doesn't seem as easy as y equals 2x squared plus 1. That was a nice sort of feature in there. Another thing is, this thing didn't depend on y, which was attractive. But as soon as we got here, and then as soon as we started to set this up, and we saw this happening, you start to get the sense, oh, this is harder. So sometimes when we do the problem, if one's getting very hard, you need to take a look at the other. Okay? There's not a really easy set of robust rules where at the beginning, these are the following things, and if they're true, you do it this way versus the other way. This was the maybe more straightforward relationship between the two. The overall function didn't depend on y, so making y the thing we were integrating over the surface on was attractive, but it wasn't super obvious. Okay. What does become obvious as soon as you get into the setup, you don't have to keep going past here to go, this looks difficult, I should try the other way. Okay. Now, this idea of doing surface integration now is common to a bunch of things we're going to do. We're going to talk about flux integration, which is a special kind of surface integration for a vector field. We're going to take the normal component of it and integrate. Then we're going to have Stokes' theorem, where we relate a surface integral value, a flux, to a contour integral around it. And then later on, we're going to do closed flux integrals and relate that to divergence. So this surface integration thing is very central to all the things we're going to do to finish off vector calculus.